Hi, welcome to the ninth session on inner product spaces, IPS 9. In the last lecture, given a basis of a finite dimensional inner product space, we showed how to construct an orthonormal basis by employing what is known as Gram-Schmidt process. Okay, so this is it's a basis with some extra conditions. But what is the use? How to use it? Okay, this is going to be the theme of today's lecture. Okay, so let us go ahead and start. Yeah. So we are ready. So let this be a finite dimensional inner product space over the field F. Field is RC. Okay. So let U1, UN be an orthonormal basis. I will denote it by O.N.basis. Let me just check. I had start the recording. Yeah, it's okay. Right. Okay. So let's recall, what does this mean? This means that if you have inner product UI uj is delta ij. That means ui dot ui is 1 and ui dot uj is 0 if I is not equal to j. This is what we mean by orthonormal basis. Alright. Now in any general thing, if you have so if you have any vector space, since this is u1 u2 un is a basis, we know given any vector v in V, there exists scalars, call them xi in F, such that v equal to summation xi vi, I equal to 1 to n. Right? We only know there exists scalars, but remember this is an orthonormal basis. Okay, this is an orthonormal basis. Okay, so my question is, can I explicitly find xi? You understand? So fix R, and can I find XR? That's a question. That means in this expression v equal to summation I equal to 1 to n xi vi, I just want to find out what is the coefficient of VR, namely XR. Now how do I do that? The one way is to kill all other xi when I is not equal to R and retain only XR. Now you know how to do that. Yeah, how will you do that? You take the inner product of V with the UR, then let us see, this is UI. Okay, UR, this is by definition summation xi ui inner product with UR, but that you know is the summation comes out inner product xi ui UR, but that is again xi comes out, therefore it is inner product ui with UR, but this you know is delta IR. Okay, since R is fixed, so this equal to 1 only if I equal to R, otherwise is 0, therefore this number is nothing other than XR. Right? So what do you think I have found? This is the first use. So this is the first use of orthonormal basis. So what does it say is that, okay, V is summation I ui I equal to 1 to n, but my xi is, I know what it is. It's the inner product of V with ui. Okay, therefore xi is vui. Okay, that's one thing. So we have found out what the coefficients xi are very explicitly. Okay, pause, review, proceed. Okay, so we have done it. Is that all? There is something very interesting. Let me see whether I have a color pencil here. Yeah, but let us look at this fellow. Oh, okay, this is not what I want, so I don't seem to have it here. So let me just go back. Okay, yeah, there is a color pencil. Yeah, right, medium thick, extra thick, highlighter setting. Okay, let me just make a highlighter. Look at this object. Do you understand what it is? You should know this is nothing other than the ith term. This is ith term, ith sum and ith term. Okay, this fellow v ui is nothing other than pi of v, where pi of v is the orthogonal projection of v on to the subspace is f times ui, the one-dimensional subspace. Yeah. So something very interesting. So what have we done? So now there is a fantastic geometry. Namely, any vector v is written as some vi, okay, I equal to 1 to n, so that vi, okay, vj is 0 if I is not equal to j. That is, we have written as a sum of vectors such that any two distinct vectors are mutually perpendicular to each other. That is, we have written v. Again, this you should know. Okay, to think of geometrically, just look at that. In the case of Rn, we had already seen that, but let me just do it only in the case of R2. This is my v. Okay, then I wrote it as a sum of, this is my v1 and this is my v2, and therefore v I wrote as sum of v1 plus v2, and v1 and v2 are mutually perpendicular. Okay, do you enjoy this geometry? These are the things you usually miss, okay, in a typical algebra course. So enjoy the geometry. Okay, that's the first thing. Okay, now what is the second application? Second application is, suppose v is summation xi ui I equal to 1 to n, and w is summation, let me write it, yj uj j equal to 1 to n, both are vectors in v, right? Therefore now I can ask, what is the inner product v with w? Yeah, see, now this is a very interesting thing. You see that? So what we are going to do is something very easy. So let us look at, you know how to do that. So let me go to the next page. I do not know how to go to the next page here, except by, if I do page down, I think I will go. Okay, right. So inner product v with w is by definition inner product of summation xi ui summation yj uj. Remember, I and j ran from only 1 to n, but I had already explained many times why I want to use different indices I and j there, right? Okay, I hope all of you know that. Now we have our usual bilinearity condition, but what I loosely call as distributive law kind of thing. Therefore this fellow, okay, is going to be, okay, call this as a vector, okay, something like let us say this is a vector alpha, this is a vector beta, then this is, I can write it as alpha, that is summation xi ui I equal to 1 to n, Okay, this is your alpha. Therefore, this, let me write it. This is alpha with the summation yj uj, right? Alpha summation yj uj, right? But this by the, we know this is nothing other than by distributive law, alpha yj uj and summation over j. Okay, but remember, the yj comes out. How does it come out? It comes out as yj bar or as yj, j equal to 1 to n. Okay, yj into alpha uj, but yj bar, right? Now, if the vector space is over R, so then yj will be real number, and therefore yj bar will be same as yj. There is no problem. But if B is a vector space over C, then yj comes as yj bar. That's a complex conjugate again there. So therefore, I can use uniform notation yj bar. I don't have to worry about whether it is it's the inner product space over R or over C. Do you understand that? Very good. Now I can do that. So I have summation j equal to 1 to n yj bar into summation. Okay, this is what? This is summation xi ui with uj. Yeah? Right. But what is that? That is going to be again by the same kind of rule. This is going to be summation j equal to 1 to n yj bar, and this xi comes out, therefore summation over I xi and inner product ui with uj. Now notice that the j is fixed, therefore ui inner product uj, this is delta ij, and since j is fixed, this makes sense only if xi I equal to j. Are you following? This object will only be the sum, this entire sum is only xj. Yeah? Are you sure? Okay. Therefore, this object inner product v with w, you see that is yj bar xj, j equal to 1 to n, which is same as xj yj bar, j equal to 1 to n. Yeah? In particular, what is norm of v squared? That is summation, inner product v with v. Therefore, that is nothing other than summation mod xj squared, j equal to 1 to n. Yeah? So, this is the second observation about the use of orthonormal basis. If I have write v as a linear combination of orthonormal basis and w also in a similar way, then the inner product turns out to be very easy. Yeah? Very good. Okay. This should not be surprising. Do you see why this should not be surprising? This is how you have to keep thinking. Why? Because remember we wrote v as summation vj j equal to 1 to n, and we said vj are mutually orthogonal, mutually perpendicular. Or orthogonal, right? And we had already proved the so-called Pythagoras theorem for a finite set of orthogonal vectors. Okay, do you recall that? What you said is v1, v2, vk is a finite set of orthogonal vectors. Okay, then summation vj, okay, its norm squared equal to summation norm vj squared. I just want you to think, okay, don't get confused. These things are never explained, so you may get confused, but don't get that, okay? So, right, therefore, now I write v as vj, and what is vj? It is inner product v with uj and uj, right? And these are mutually orthogonal. Therefore, by Pythagoras theorem we had already seen is norm of v squared equal to summation norm of vj squared. But what is vj? This. Therefore, what is vj squared, norm of vj squared? This is nothing other than this one. Remember, this is nothing other than your xj, right? Therefore, mod xj squared, and remember uj's are unit norm. Therefore, this is this. Therefore, that is equal to mod xj squared. Okay, we had already derived it, but you have to, as I keep saying, you have learned something, you should relate, because textbooks do not explain v when you write it as summation xi vi. Okay, then xi ui, then xi ui is nothing other than orthogonal projection of v onto ui, the space spanned by ui, right? That geometry is never brought out usually, right? Now, if I have a sum of orthogonal vectors, we know how to find the norm squared. That is Pythagoras theorem. So it comes out. Okay, just this kind of playing makes you very comfortable with that. Okay, right. And now we will come to, let me look at PR, insert PRP. Now let's go to the third. The third thing is the following. So this is a very general. Okay, this is a general case, no inner product. Okay, it's essentially a recall or review of something. Suppose V is a finite-dimensional vector space over a field F, any field. Okay, and suppose V1 to Vn is a basis. Okay, it's just a vector space. Okay, nothing to do with it. May not be vector space or RRC. To talk about inner product space, I need a vector. The field should be RRC. Remember that. Okay, this is just our abstract vector space, right? Then we write x equal to summation xi vi. This is a unique linear combination. Now, therefore, I can associate V with an n-tuple x1 to xn, and notice that this is a well-defined function because these x's are unique. Therefore, I have a map from V to Fn. Okay. So, if you have gone through linear algebra well, or if you have watched my videos, you know this is a linear isomorphism. This map is a linear isomorphism. Call it here. This is a linear isomorphism. Is that clear? Quickly go through. Okay. If you are in doubt, this is a kind of place where I will again check why it is linear. Because if V is xi vi, W is yi vi, then x plus V plus W will be xi vi plus yi vi, that is xi plus yi vi. Okay, why this is correct? Because the uniqueness of the expression. Therefore, V plus W, what is the corresponding n-tuple? x1 plus y1, comma, etc., xn plus yn. All this kind of thing you should go through. Okay, just don't accept it. Okay, whenever these kind of small things come, I repeatedly tell you, you just pause and review how the proof went. Quickly, don't go through all the arguments, just quickly see that. You will see, you don't have to remember anything as you keep doing. It will be automatic for you. Like the way multiplication table is automatic for you now. Okay, right? Now come back. So the next question I can ask is the following. Suppose V, this is an inner finite dimensional inner product space. Okay, let U1 to Un be an orthonormal basis. So we again have the map F from V to Fn. Now this Fn is Rn or Cn, right? Okay. So what is the map? We going to x1 to xn. F V is summation xi vi, right? Okay. So we know this is a linear isomorphism, right? Now I can ask something very interesting question. Suppose I take V and W in V, and let's look at the inner product VW. Suppose V is this and W is summation uj uj xi I equal to 1 to n. Yeah, remember U1 U2n is orthonormal basis. I wrote Vi by mistake. We know this is nothing other than xi yi bar. This we already saw, right? This is what we saw in the third thing. Okay. You see this? Yeah, that's what I am using. Maybe I should highlight just like that, so that it will be easier for you. Yeah, very good. Now come back. Right? Now, do you find something very interesting? Yeah. The interesting thing is the following. Okay. What is f of v? F of v is the ordered n tuple x into xn. F of w is the ordered n tuple y to yn. These are vectors in fn. And therefore, what is the standard dot product on fn? The standard dot product on fn is xj yj bar equal to 1 to n. But this is nothing other than the inner product vw. Right? So what is that you assume? That f, which is a linear map from with to this to fn to the dot product, this thing up here is a dot product, okay? Not a multiplication or anything. I am saying using this notation for dot product, right? So we going to v of u1, v of u2, that is your x2. Do you remember that? V of un. I am just writing in different ways so that you should not get psyched, okay? Because what is our xi? It is v inner product ui. So I am just writing that, okay? This is how you just have to keep relating. Okay, this is not only a linear isomorphism with an additional property. With an additional property. What is that? It preserves the inner product. For all v and w in v, okay, the inner product of fp, the dot product of fp with fw is same as the inner product of vw. That is, we say f is inner product preserves inner product. One usually says it preserves inner product. What does that mean? Again, have a picture. This is a very trivial picture. What you have is something like this. Okay, this is your v, and this may be w, and the length and the angle, whatever it may mean, that is, this is your fn. This is your v, and it may go like this. It may go like this, but the length is preserved. The angle is preserved. Remember, in the complex vector space, we are defined only perpendicularity. No angle is defined. But intuitively, I would think it preserves the structure. Is that okay? Yeah. Pause, review, proceed. Whereas in the real inner product space, there is an angle defined. It also preserves the length as well as the angle. Okay? Very good. The next one is the fourth, or is it fourth or fifth? I do not know, but let me just keep this. Yeah, this is the third. Yeah? Third, yeah. It's a linear isomorphism addition. Okay, now this is the fourth one. What is the fourth one? Fourth one is, let us assume these are inner product spaces, finite dimensional inner product spaces. Let u1 to um and v1 to vn be orthonormal basis. This is orthonormal basis for this. This is orthonormal basis for this. Right? This is m-dimensional. This is n-dimensional. Okay, good. Now, suppose f is a linear map from v to w. Since this is the u1 u2 em is an ordered basis and v1 v2 n is an ordered basis of w, we know how to write down the matrix of f with respect to the ordered basis. Okay, right. We know how to find. Let me quickly recall in case you have forgotten. It says if I take Vj, okay, j equal to 1 to m, okay, then let us look at f of Vj, and that is a vector in W. Write it as a linear combination of basic vectors. Right, so remember that. So here I am writing v1 to vm, so let me just call this v1 to vm, w1 to wn. Okay, because v sitting in w sounds a little peculiar to me. I hope you don't mind now by changing, right? This will be a linear combination of vectors in the basic vectors in wi, therefore it is going to be this is going to be linear combination of wi, that is going to be, I will write it as a I j, and this is I equal to 1 to n, right? Then this vectors, namely a 1j, a 2j and a nj, okay, these coefficients form the jth column of this matrix. Okay, I am just again recalling you, because many times I find students just learn just how to write down the matrix, but they don't remember that. This is the very geometric way of looking at. And notice that usually I write the other way around. I write it a way different from what your usual teachers would write. This is Vj and you see the Ij. Therefore, it becomes the jth column. Okay, is that clear? Okay. Okay, let me again write it in this page. Therefore, f of Vj is summation a I j and wi I equal to 1 to m. So this is a vector in W. I wrote it as a linear combination of the basic vectors wi, but wi are not just any basic vector, they are orthonormal basis. Therefore, I know what these coefficients a, j are. Do you remember that? They are nothing other than take this vector and take its inner product with wi. That's it. Therefore, this fellow is nothing other than f of Vj inner product with wi and wi. I equal to 1 to n. Just pause, review this. Okay, do you understand how I wrote this? Okay, we wrote the very first observation, very first use of orthonormal basis. That fact I use. F of Vj, I want to write as linear combination of wi, where wi form an orthonormal basis. That means take f of Vj, take its inner product with ith basic vector. That's it. That's what we did. Isn't it beautiful? Right? Therefore, I know what is the jth column. Jth column, I know now explicitly. What is that? That is going to be f of v1 inner product with wj, f of v2 inner product with wj, and f of vm inner product with wj. This is your jth column of the matrix. Yeah, I understood. Therefore, I know how to write down the complete matrix now. So how will I write down the complete matrix? Right, I will start with, I'm sorry, this is wi. I'm very sorry, this is the wi, f of vj. I'm sorry, I made a mistake. This is wrong. Wrong. Let me repeat. So jth column is, okay, jth column, how do I get? F of Vj inner product with W1 and F of Vj with W2 and so on, F of Vj with Wn. This is the jth curve. Yeah? Right. There is a call, let me just check. Okay, right. I hope all of you understand this. Therefore, you know how to write down the entire matrix. Therefore, the entire matrix will be F of V1 inner product W1, F of again V1 inner product W2 and so on, F of Vm V1. Now I lost my cursor. Yeah, F of V1 inner product with Wn, and the last one will be F of Vm inner product with W1 and F of Vm inner product Wn. Okay, this is the first column, this is the mth column. Alright, therefore it's a matrix of size and cross up. Is that clear? So pause, review, proceed. Okay, now we are coming to the last thing. Okay, this is again a review. So when we dealt with linear maps, one of the first examples I looked at was, I think perhaps the second example. Suppose here F is from Rn to R is a linear map, then we identified all linear maps. All linear maps F from Rn to Rn. The same proof was through for any Fn to Fr. So, but in my linear maps lectures, I looked at only Rn case. Okay, how did you do that? Let us look at the standard. Any basic vectors E1 to En. Then, if I start with a vector x equal to summation xi ei, then f of x is going to be xi f of ei. Right? Suppose I call this vi as, let us say, ai. Right? You notice that this is nothing other than x dot a, where a is the vector a1 to an in Rn, and this is nothing other than dot product. Right? This we have seen. Okay. So here any linear map is of the form summation AIXI. That's all we proved there. Now we know that. But what I am saying is I am trying to reinterpret. Now that we know inner product, there is a dot. In the case of Rn, it's a dot product. I can think of xi multiplied by a as x dot a for summation. You follow that? Therefore, I can rewrite this in the case of Rn. This is what we proved. Any linear map F from Rn to R is of the form f of x equal to x dot a for a vector a, where a equal to a1 to an, and my a is f of a. Okay. So pause, review, proceed. Now I want to generalize this. So let V be a finite dimensional vector space as usual, as earlier. Right? What do I want? Let F be a linear map F from U to F. Now F is RRC. This is a linear map. So what do I want to show? I want to show there exists, we have vector V in V, so that for all, okay, let me say for all, okay, let me write V naught in V, so that for all V in V, F of V is V inner product V naught. So these are all the only, so therefore if you give me a linear map from inner product space to the ground plane, it is given by, there is a unique vector, we will see that's unique later. There is a vector V naught, so that F of V is got by taking inner product of V with V naught. Please understand, this is beautiful. You classified everything, and it is intimately related to the additional structure on the vector space, namely inner product space structure. Okay, right. Now how do I prove that? There will be a geometric proof which I will give later. Okay, but now I will proceed algebraically. Okay, let us work backwards. Okay, so assume such a W0 exists. Right. Now remember my U1 to UN is an orthonormal basis. This is my standard notation now. Right. Therefore my V0 I can write it as, let us say, summation Ci Ui I equal to 1 to n. Right. Therefore finding V0 is equivalent to finding Ci's. Right. So knowing or finding V0 is equivalent to finding Ci, right? But that's very easy, because what is Ci? You already know. If I write V0 as summation Ci Vi is the orthogonal projection of V0 onto the one-dimensional subspace spanned by Ui. Right, and therefore the Ci is given by V0 inner product with Ui. Do you remember that? Yeah. So let us go slow. Okay. So now we want to find right, that we know how to do that. Okay, to find that what we need is this thing. Okay, let V0 equal to summation Ci Ui I equal to 1 to n. Now we have to make use of the fact, what is the property of V0? For any V, okay, f of V is given by inner product V with V0. Now I want to find Ci, right? So what do you think will be the obvious way to do that? Okay, I know the linear map F. As soon as I know its action on any basic vector, in particular on the orthonormal basis. So let us do it. Therefore, what is f of Ui? F of Ui is by definition, since V0 satisfies that property, it is Ui in inner product V0. Okay, this is by our assumption about V0. Okay, we are using the hypothesis on V0. But what is this? This is summation Ui, inner product Ui with summation. Okay, since I used to Cj, let me write it. Cr Ur are equal to 1 to n. Right? But this again, now that all of you are good, this is going to be this summation will come out. Therefore, it is Ui with the Cr Ur are equal to 1 to n. But that is equal to summation r equal to 1 to n, and this Cr is in the second factor, therefore it will come as Cr bar. Remember again, if it is a real inner product space, Cr will be real, therefore Cr bar will be same as Cr. So I don't have to distinguish whether the inner product space is over R or C. I can always use the bar in the second variable. When I take the scalar in the second variable, I can use the bar without any problem. Please understand, these are the beautiful things you should understand. Therefore, this is nothing other than now Ui with Ur. Right? Now Is fixed, R is varying, therefore the only surviving term will be Ci bar. Right? Ci bar. See, that's why I didn't want to use I, but I keep forgetting. The bar is over the Ci bar. That's a complex number, it's bar, not Ci bar. Okay, Ci bar by Ci of minus I, which makes no sense. Okay, that's for fun. Okay, right? Therefore, I know what is Ci. Ci is nothing other than f of Ui bar. Therefore, my vector V0 is some f of Ui bar Ui I equal to 1 to n. Okay, now working backwards, you found a V0. You understand? But you really have to check whether this v0 works. But you just have to work backwards. Are you following? So, working backward, we found a candidate. Namely, v0 is given by summation f of ui bar ui I equal to 1 here. Okay. So I want to know whether, therefore I want to know for any v, f of v, is it equal to v0. This is what I have to check now. Okay, therefore to check, we have to verify now this v0 does the job. Okay. Are you following? Okay. But since both notice that this map v going to v inner product v0, remember this second variable is fixed, therefore this is also linear. This we already know. Now you see that why I want to write v0 in the second variable, not in the first variable. So these are the things which teachers will not say, thinking that my students will get confused. But you should understand, right? Suppose I want to write f of v equal to v0 v. In the real case it does not matter. In the complex case there will be a problem because of complex conjugation, right? If I put a lambda here, lambda will come as lambda bar. Okay, f of lambda v will be v0 with the lambda v, but therefore the lambda will come as lambda bar, so that won't work. Okay, this is an aside, don't get confused, think about it. So f of lambda v does not come out as lambda into f of v. It comes as lambda bar f of v. So that is the reason why we put v0 in the second variable. Okay, this is linear. This is all right because the inner product is bilinear. So if I fix the second variable, it becomes linear. Sorry, it's not bilinear. Okay, it's a linear in the first variable, conjugate linear in the second variable, and second variable fixed, therefore it is linear. Fine. Okay. Therefore, to check, so call this as a linear map G. F and G are linear maps from where to where? B to F. They are both are linear. So to show F equal to G, it's enough if we show F of UR equal to G of UR. Okay, for R less than equal to 1 less than equal to R less than equal to n. Because two linear maps, if they agree on a basic basis, they agree everywhere, right? That's what I have to check. Okay, these are actually we checked, but it's just to be on safer side. Okay, because algebra teacher may usually start with take v0 equal to this and he will verify. So that's the verification we are doing. You should know what we are doing. Okay, but what is f of VR? F of VR is nothing other than, we know according to our definition it is CR bar. Remember that? Ci f of UR bar is CR, therefore f of UR is CR bar, right? But that is CR bar. But what is G of UR? G of UR is, okay, inner product of UR with the summation Ci UI, right? That is your V0. You understand that? So what does it come? This comes out as, again, by the usual thing, this comes out as summation Ci bar inner product UR with UI, and this summation is for I, therefore only CR bar, therefore f of VR equal to G of UR. Are you convinced? Yeah? Okay. So what then we have shown? We have shown that if F is a linear map from V to F, there exists a V0 in V, so that for all vectors V in V, F of V is inner product. What should be come in the first variable? Not V0. V0 should come with the second variable. Why? Because in the complex conjugate case, linearity is assured only in the first variable. Okay, keep that in mind. Now I want to know whether it's unique. Okay, does there exist, let us say, w in V, so that f of V is also VW for all V. Okay, if that be the case, what do you want to say? You want to say W and V0 are the same. Yeah, right. But that's very easy to do that. Suppose f of, okay, this happened, there is a W, so that this happened, then these two are equal. Since these two are equal, that means V0 must be equal to VW for every vector V in V. Right? Now bring it to the other side, therefore this minus this must be 0. Right? Now again use the additivity in the first variable, etc. Therefore this is V0 minus W is 0. Right? This object is nothing other than that, using our intuitively distributive law or additivity. Yeah? This is true for what? For every V. Okay, in particular, take V equal to the vector V0 minus W. Then this becomes V0 minus W, V0 minus W is 0. By the definition of inner product, that means V0 minus W is 0. That means V0 equal to W. Therefore, we have proved uniqueness. Okay, so pause, review and proceed. Okay, these are the uses of orthonormal basis. I hope you enjoyed. Okay, and I also brought out the geometry. Please go through once again. And whenever there is a small thing which you are using what we learned earlier, I repeat once again, stop and quickly go through the proof. Okay, not with all detail. You will see you can think through a proof at any time. You don't need notes or a textbook or a small sheet, okay, to peep into. You can do on your own. I hope you enjoyed. We will meet again.